Hello, my dear students. Today we'll see semiconductor devices, semiconductor materials, and then we are going to add on some simple circuits also. So it is the chapter given in your class 12 NCRT. So we'll see that today. Now, so before we move into the chapter, I will give you a brief summary. Energy bands and conductors, semiconductors, insulators, these are all we are going to study. Only qualitative ideas, so not fully. And then intrinsic and extrinsic semiconductors, P and N type semiconductors, that is intrinsic and extrinsic. Then PN junction diode, semiconductor diode, it's VI characteristics, that means voltage and current characteristics in forward and reverse bias. So both are we are going to see. Then application of that junction diode, that is the diode as a rectifier. Okay. So full wave rectifier and half wave rectifier. These are all we are going to see. Here, before the discovery of transistor, devices such as vacuum diode were used to control the flow of electrons. Okay. In a circuit, I'm talking about. But these devices were bulky and consumed high power, operated at high voltages, and had limited life and low reliability. Okay, in the 1930s, it was realized that solid state semiconductors and their junction offered the possibility of controlling the flow of charge carriers through them. So this led to the development of the modern solid state semiconductors. They consume less power, small in size, operate at low voltages also, and have a long life and high reliability. So this is what you must understand, the futuristic, I mean, factors and everything. So this is how the technology is improving. So during 1930s only, semiconductor, solid state semiconductor electronics goes back. Okay, modern thing. So it is given. Okay, so you know that classification of all the materials like metals, conductors, and semiconductors. Okay, you must understand. You know the metals, right? In your book, it is given. The resistivity is given. Okay, so metals are specified to conduct freely. Okay, so metals are good conductor of heat and electricity. So it has high conductivity and very low resistivity. So resistivity for the metals are given. What is this rho? Rho is the resistivity, sigma is the conductivity. Okay, so rho is given the value 10 per minus 2 to 10 per minus 8 ohm meter. Then steradian, S is steradian. So conductivity, you know, right? Siemens, it is talk about the Siemens per meter. Okay, this is ohm per meter, this is Siemens per meter. Okay, then semiconductors. When you talk about the semiconductor, resistivity and conductivity lies in between that of the conductors and the insulators. You know the insulators also. It is having very high resistivity, very low conductivity, right? So its rho is 10 per 11. Resistivity is see 10 per plus 11. See the resistivity of metals maximum 10 per minus 2 and 10 per minus 8 like that. It is 10 per 9, 11 to 10 per 19. Resistance are very high in the insulator. So it doesn't allow the charges to flow through. So sigma is conductivity is very less when compared to this. You can compare and put a table, comparative chart, so that it is easy for you to keep everything into your mind. Okay, the semiconductors lies in between. Okay, so rho is this the conduct resistivity is 10 per minus 5 to 10 per plus 6 ohm meter. Okay, then conductivity is 10 per 5 to 10 per minus 6 Siemens per meter. Just keep everything into your mind. Okay, you know the formula also. How this rho comes, right? That is also enough. R is equal to rho L by E. So everything you have learned. Okay. So elemental semiconductors, about the semiconductors, the metals or conductors, copper, nickel, etc. We can say semiconductors are silicon and germanium. Okay, maximum elemental semiconductors are silicon and germanium. There are some compound semiconductors also. Examples it is given. Okay, so these are all the compoundal. Go through it. It's very simple one. And the insulators are wood, rubber, etc. Then you must know. eh, Then there are organic and organic polymers. Everything it is given, right? Doping is the new word you are going to learn about here. I will explain you in further. Okay. So after 1990, a few semiconductor devices using organic semiconductors and semiconducting polymers have been developed, signaling the birth of a futuristic technology of polymer electronics. Okay. So it is given what is meant by energy bands. For example, on the basis of energy bands, according to Bohr's model, every electron of an isolated atom has well-defined energy levels, right? So each and every electrons are occupied in various energy levels. But when the atoms come together to form a solid, they are very closely packed, close to each other. So the energy levels of the electrons from neighboring atoms will become very close or would even overlap. So these different energy levels with continuous variation forms, or continuous variation, it is called energy bands, we can say. Okay. So the energy band, which contains the energy levels of valence electrons, is known as valence band. This is the lower energy band. This band is never empty. Definitely, it is having electrons. The energy band above the valence band is called the conduction band. Normally, the conduction band is empty. When it overlaps on the valence band electrons, okay, when it overlaps on the valence band, then what happens? Electron can move freely into it. This is the case with metallic conductors. In the metallic conductors, you may see the energy bands are overlapped. Okay. There is a separation between the highest energy level of valence band and the lowest energy level of conduction band. That is known as energy band gap. So I'm going to show you the picture. This is that picture. Okay. So that separation is known as energy band gap. It may be large, small, or even zero, depending upon the material. Okay. So how the overlapping takes place, everything it is given in the subsequent pictures. You can see the picture here. Okay. So the energy gap also given. What is the first picture demonstrate about metals, right? So metals differentiate between energy bands of metals, insulators, and semiconductors, right? A is metals. See, this is valence band. This is conduction band, right? Okay. So valence band, the top of the valence band and the bottom of the conduction band, okay, has the electron transfer. Hmm? Sometimes it may overlap also. That is Eg is almost equal to zero. Okay. Suppose if the energy band gap is very much greater than 3 electron volt, we are talking about the energy. Okay. It is in electron volt. Hmm. If the energy band gap is 3 electron volt or more than 3 electron volt, then it is acted as an insulator. For an insulator, it will be like that. If it is very much less than 3 electron volt, then that is semiconductors. Okay, these are all illustrated in this. So energy gap is very large that electrons cannot be excited from the valence band to the conduction band by thermal excitation. Okay, so that's what it is an insulator. Insulators have the large energy gap so that the electron cannot be excited from the valence band to the conduction band. You know, right? We have learned about in atomic structure in atoms, the electrons, outermost electrons absorb energy from the source and then it moves to higher excited level. So according to Bohr's orbit, right? So that is, Planck also actually he demonstrated the excited energy, right? From E2 minus E1, the amount of energy radiated is equal to H nu. That and all you have learned, right? So that excited level, after it reaches its excited level, it can't stay in that level for a long time. So it turns back to its original state by releasing the amount of energy what it is absorbed. Okay, so we are talking about this energy gap only, energy level difference. Okay, so when you talk about a single electron, single atom, it is okay. But if it is grouped with, if it is a solid, it is grouped with so many atoms. So various level of energy bands are there. So we are grouping valence band and conduction band. In between, there is a gap. If the gap is very, very small, even it is zero, then that is conductor. The gap is almost there and less than equal to 3 electron volt, then that is semiconductor. If it is greater than 3 electron volt, then that is insulators. Okay, that's all in this. Then intrinsic semiconductor. This is very interesting. Now only you are going to learn about the intrinsic semiconductor, right? So before that, you don't know what is intrinsic and extrinsic semiconductor. Okay. So first of all, you must know about holes and electrons in semiconductors. You know, in an atom, how the electrons are revolving around the nucleus in various orbits, you know. So if the electron is, if an atom, every atom of a metal has the tendency to lose an electron. If an atom loses an electron, then the atom becomes ion, positively charged ion, cation. Okay, and the electron which is attracted by some other atom, which is having in order to maintain its octet configuration, then that is known as anion. So cation and anions, that is positive charge and negative charge, like that we have come across. You know about the atoms, right? So here in semiconductors, in metals, that is the case. That's what you have learned. The electrical, electrostatics and electrical currents, right? So electrostatics, you have learned about the electric field and the charges, and charges are quantized and everything. In current, you have learned about the free electrons. The free electrons are responsible for the current. But in a conductor, the case is like that. If it is a semiconductor, holes and electrons are the types of charge carriers. Okay. So what are the holes? What are the electrons? We know we need to understand. Okay. So we shall take the common case of germanium and silicon here. It is the lattice structure shown. Okay. Three-dimensional diamond-like crystal structure for carbon, silicon or germanium with respective lattice spacing A equal to like this. Okay. So you must understand the crystal structure you did. Actually, that chapter was deleted for you. The crystal structure, or you can say a point, at that point where the group of atoms are arranged in a proper manner, that same pattern is repeated in each and every uh, space or in a corners of a cube. See, for example, we can say it is a regular, repetitive, periodic arrangement of group of atoms. The point where the group of atoms are arranged is the lattice point, and the space in between two lattice points are the lattice space. Okay. So you must understand the lattice space. Okay. Say, for example, for a carbon, what is the lattice spacing? Lattice spacing is 3.56. For a silicon, 5.43. For germanium, it is 5.66. Okay. So everything is here. We know that germanium and silicon have four valence electrons, right? Including carbon also. In its crystalline structure, every silicon or germanium atom tends to share one of its four electrons. Okay. With each of its four nearest neighbor atoms. This is the different case of silicon and germanium. Okay. Not in carbon. Okay. Then these shared electron pairs are referred to as forming a covalent bond. or simply a valence bond. For example, four nearest neighbor atoms should be there, and also to take share of one electron from each such a neighbor. So it forms a covalent, two mutually shared pair of electrons. Okay, two shared electrons can be assumed to shuttle back and forth between the associated atoms, holding them together strongly. Okay, so the 2D representation of silicon or germanium structure is given in the picture, which overemphasizes the covalent bond. So it showed an idealized picture in which no bonds are broken. Such a situation arises at low temperature only. As the temperature increases, definitely the thermal energy becomes available to these electrons, and some of these electrons may actually break away, okay, by absorbing the energy, okay, thermal energy, and becomes free electrons, contributing to the conduction. Got it? This is what happening. Okay, the normal energy effectively ionizes only a few atoms in the crystalline lattice and creates a vacancy in the bond. Okay, the neighborhood from which the free electron charge minus q has come out leaves a vacancy with an effective charge plus q. I will explain you this. Okay, if an electron leaves from that site, that vacant site is known as the hole. I told you, right? The electrons in the holes must be learned in this semiconductor part. Okay, the hole behaves as an apparent free particle, the hole is, so that it can be reaccommodated by the electrons. Okay, so it is an active particle, kind of free particle. Okay, see, this electron also free electron right now. Okay, after absorbing the thermal energy. Is it clear for you? Then okay, so it is effective positive charge. So why it is known as positive charge? It can be reaccommodated by the electron. So electrons gets naturally attracted towards the positive charge. Okay, so we consider this vacant site or hole as a positive charge. So the hole and the electrons are the charge carriers here in a semiconductors. Got it? Then I'll explain you in the energy band diagram. It is given in your book very clearly. So then, in an intrinsic semiconductors, the number of free electrons, Ne, is equal to the number of holes, NH, that is here, like this. So that means what they are trying to say in a pure semiconductor, intrinsic means pure semiconductor. It is not mixed up with some other materials. If the pure semiconductor is mixed up with some other material, then what will happen? Definitely that mixed up nature is known as doping. Okay, if a semiconductor, pure semiconductor, is doped with some other materials, monovalent, trivalent, pentavalent compounds, then what happens? It will become an extrinsic semiconductor. Okay, so actually, in order to behave like a charged material, that means in order to get the free electrons and the holes, the material or the system has to be kept in temperature. So it needs definitely a temperature. It should be under some temperature. Okay, the temperature is needed for the material to become holes and electrons. Okay, to produce charges, kind of. But if it is a pure semiconductor, it has to be heated, and the energy has to be added in the form of heat. Okay, when energy is added in the form of heat, few electrons, only it can cause a few electrons to break free of their bonds, not the full electrons. So in the topmost valence bond, you can say very few electrons are free. Okay, and then it is about to move to the conduction band. Is it clear for you? Not all the electrons, so that it leaves the vacant side. So holes are there. So only very few holes and few electrons are formed in the ratio of number of electrons should be number of equal to number of holes. So how many electrons are transferred to the conduction band? The same holes are left behind. Okay, so that is shown clearly here. See, this is the effective, valence band energy. This is conduction band energy. This is the energy gap. The electron has to move from here to here, like this. If it is kept in a temperature, when it is T is equal to 0 Kelvin, no electrons are found in the conduction band. that is not leaving from the valence band. It doesn't have much energy to move to the higher excited level. Okay, that is the case. Because EV is like a ground state, like EC is the conduction state, that is the excited state. Okay. So if the temperature is increased, then what will happen? You may see few electrons moves to conduction back, leaving the sites, vacant sites, that is called the hole. Got it? So here these are all the free carriers, charge carriers, we can say electrons and holes. Okay. Is it clear for you? So that the material has to be doped with some other atoms. So we are going to see that in an extrinsic semiconductor. So intrinsic is highly, expensive. In order to keep that in a temperature, then that has to be maintained in the perfect laboratory equipments and everything. So if you add it, or if the material is doped with some other materials, the semiconductor is based on its, valency. So we can able to find out the extrinsic semiconductor, which is highly commercial, and then it is useful. Okay. So these electrons are thermally generated free electrons, we can say. Okay. So it is having both the current IE plus IH. It is also very important. Can go through it. So what I have explained you, it is given here. Okay. So both the currents are there. Since it is, you know that it is not like a proton and electron. See, again and again, I'm saying to my students, we couldn't take one proton out from the nucleus. Okay, you are considering if the copper is losing two electrons, you consider that copper 2 plus ion as a positive charge. Okay, and then remaining are the negative charge, that is the electrons. Okay, but here the holes are active, and then it can move, it can accommodate the electrons also again. Okay, the electrons can be re-accommodate into that particular hole. So we talk about the holes also moving. So if it is moves, then definitely it is associated with current. So here two currents are there. One is electron current, another one is hole current. So that is the total conduction current. Holes can be recombined with the electrons. Based on that, the electron also, the holes also moving. It is given here. Okay. Then extrinsic semiconductor. I told you about the extrinsic semiconductor, right? How the extrinsic semiconductor behaves and everything. And then this clearly you have to learn what is this? This is the site. Okay. For example, this is silicon. Silicon has four electrons. Okay. So how this four electron can be shared between some other atoms. Okay, in between. See here. Like this it will be. If you look at the center, see, two, like that. Here you may found the hole, right? Since the electrons leave this particular site, and then it creates a hole here. Okay, this plus force indicates either silicon or germanium. Okay, so thermally generated free electrons are there. So this is how it is bonded with, like a covalent bonding. Okay, then here also you can see. So this is talk about first one, schematic model of generation of hole at site one and conduction electron due to thermal energy at moderate temperatures. Next one, simplified representation of possible thermal motion of a hole. That is also given here. The electron from the lower left-hand covalent bond, that is site 2, goes to the earlier hole site 1, leaving a hole at its site, indicating an apparent movement of the hole from site 1 to site 2. So it clearly indicates the hole also moving. Okay. Okay. So from here, the hole is reduced. Okay. At the side 2, the hole is there. Now it is moving to the side 1 where the electrons are. So it can be recombined. Okay. So the hole also moving. So this is the pattern which clearly shows what? The electrons are bonded, how it is bonded in a semiconductor. Okay. So suppose if it is a germanium atom, how it is bonded with the nearby atom. If it is a silicon atom, how it is bonded with the nearby atom. I will clearly explain like this also. If it is easy for you, you can take down this picture. Okay. For example, you have drawn uh, like so atoms. Okay, you can draw silicon atoms. Okay. So here you can draw like this the bond. Okay. Like this you have to draw. First, like this, in order to explain the intrinsic semiconductor. Okay. Then you can add on electrons and holes. Okay. Hmm. Okay. Then like this. Okay. Okay. How it is bonded. Like this you have to add on. Okay. So you can notify here subsides. Site 1, site 2, like that it is given in your book. Okay. You can determine like, so suppose if you are determining this as site 1 or A site. Okay. So here the electrons are, okay, electron leave that and the hole is, if it should find the hole here. Okay. Or this is B site, like, okay. So the vice versa also can be possible. Now, after it reaches this hole, then what will happen? This becomes, after it reaches to this hole, now the B site becomes, I mean, achieves electron, or the electron is recombined in that hole, and A site is left as a hole. So both are possible. So you can see hole also, I mean, traveling, hole also moving. Okay, so there are two currents you have learned in an intrinsic semiconductor. So we'll learn about the extrinsic semiconductor in the next video. Thank you.